The Puripod air ioniser, as it's so frequently advertised on eBay, as seen on TV, silent ionic air purifier, and a lot of people are selling these as ionisers, but it's pretty clear from looking at it and the little ceramic tube inside that this is a Corona ozone generator. But the exciting thing about this one, that's very exciting, I'll just plug it in briefly, is that when you plug this one in, it's making loud electrical popping noises, and that little buzz you heard there from that is the least of it, because occasionally the lights blink on and off and it makes loud popping noise as well. And that's with the knob turned off. It's not even generating ozone at that point, so that's the high voltage circuitry theoretically off. I think it's time to open this and see what's going on inside. It's notable that one of the sort of adverts that I saw for this on YouTube, because I looked to see what they were advertising it as, described it as if it was an ioniser, and they showed the smoke test. The classic smoke test in ionisers is where you get a chamber filled with smoke and then you turn the ioniser on and it clears. In this case, they had this inside the chamber, they filled it with smoke, turned it on, and then there was a jump cut, and you could see that because they just let the smoke clear, because this won't do it. So the construction inside is very typical of these things. The fan is glued onto the back. Note that the wiring is very close to the high voltage transformer. Does anything else come near the wiring there? I don't know if that's the problem or not there. Let's unplug this. Oh, let's just pull the whole circuit board out. And take a look at the back. Anything obvious? I'm not seeing anything obvious here, though I get the feeling it might be a dry solder joint or something. I'm looking at that component there. I'm not sure if you can see that, but it's soldered at one side, not the other, but that doesn't necessarily mean anything. It's got tiny little bits of solder. I'm looking for a loose connection or something. Following it through, we've got the mains coming in here from the connector. We've got a fuse, which is not blown yet. We've got a metal oxide varistor for suppressing spikes. We've got the X2 capacitor with a discharge resistor across it. We've got the common mode suppression choke. We've got another X2 capacitor. We've got the bridge rectifier based on discrete diodes. And then we've got the smoothing capacitor here, so that basically forms a high voltage DC supply. And that suggests then that this little chip here is going to be a switch mode power supply driving this transformer, and the output, it's got opto-isolated feedback, so it will be fixed voltage output. Previous experience shows about 12 volts. Then we've got, actually, you know what, I'm going to take a picture of this and then we'll take a closer look at it. So I found where the electrical problem is. Watch this connection here on the common mode suppression choke. See that? That is a bad solder joint. Okay, we have solved the problem. It looks as though it might have been whacked in shipping or something like that. So I shall solder that and we'll take a closer look at it. The unit has now been fixed and thoroughly reverse engineered, and it really has had a bit of a rough trip at some point in its life. Looking at the back of the circuit board, these two pads on the common mode suppression choke were smashed off. There was pads had been knocked off in the suppression capacitors. Both these suppression capacitors had the pads off, and the core, rather annoyingly, is just basically all smashed up in the common mode suppression choke. So it's had a bad trip. So what I did here was, because the pads had been removed completely, I got a screwdriver and I scrubbed off some of the solder resist on the tracks next to them and then just bridged across. So that's fixed. The circuitry is quite interesting. We have the supply coming in, and it's got, the first thing it does is it goes through this fuse, and it's got this metal oxide varistor to clip any transients. It's got the class X2 capacitor. I mentioned this earlier on, but I'll go over it again. it's got the common mode suppression choke, which basically it allows, if the current's flowing in opposite direction in each leg, it's absolutely fine. But if it's interference that's coming out both legs at once, they'll actually magnetically react against each other and cancel each other out. And then it's got another X2 capacitor, and this is good. This is like a lot of suppression. It then goes through this discrete bridge rectifier based on 4 surface mount diodes, and then to this capacitor here, which is this capacitor here. The chip it's using as a switch mode power supply chip. Let me bring this in, see if it's going to swamp out. It's going to swamp out. That's all right. Let's tame it down. The power supply is an SDH8302, and they're using it to generate approximately 12 volt power supply. Most of the circuitry is as shown here. It's got the filter here, it's got the bridge rectifier. The thing that's missing here is it's just got one capacitor, it's not got the little secondary inductor. Likewise in output, they've not got the secondary inductor. This is just filtering. Everything else is there. The transformer has, let's see if I can actually point these out. The transformer has the suppressor across it's got a snubber network across the primary winding of the coil, which is this diode, this capacitor, and this resistor here. And other things worthy of note, it's got this little auxiliary winding, a sort of bootstrap winding, which powers the chip by charging, when the chip's running, it charges this capacitor here, which is the power supply for the chip. In this case, this is the bootstrap diode, and this is the capacitor. And if you look on the circuit board, it's this little capacitor here that's doing that. Looks like an ordinary capacitor. It doesn't look like a high frequency one. Could be wrong though. I'd guess it must be a high frequency one. So, or low ESR, low equivalent series resistance. You have to use those that type when you're running them at very high frequency, because otherwise the ripple causes them to heat up. The circuit shows an opto-isolator being used to control it, and it's got quite a complicated circuit. It's got the usual little TL431, is it? The little feedback circuit. But in this case, they didn't do that. Where's a pen? There's a pen. In this case, they took the positive rail and they put a Zener diode rated about 11 volts, and they put that in series with an LED in an opto-isolator with a capacitor across it. And that goes down to the 0 volt rail, or as they're drawing it there, they're drawing it as a wee sort of pointy triangle. And that is the LED in there. So it's ultra simple. It's got rid of this resistor here, this one. So it's got rid of 4 resistors, and the sensor component just replaced it with a cheap Zener diode, or Zener diode as some people prefer to say. Although apparently his family referred to him as Zener. Not so sure about that. So we've got our 12 volt supply. And now it does 2 things. It powers the fan. Let's brighten this up again. It powers the fan on this connector here. And if we look at the circuitry here, there's the Zener in series with the opto-isolator and little capacitor across it, and that's feeding back. The switch on the potentiometer that varies the output switches the fan on and off. Strangely, it doesn't switch the ozone generator on and off. So it's feeding from the positive rail, it's going through that switch, then it's going through a 68 ohm resistor, and then to the fan. The reason they've used a 68 ohm resistor is purely to nudge the speed of the fan down, because it makes it quieter and it just reduces the airflow. I think the main thing here is that if the fan was running full tilt, those little fans are just excruciatingly noisy. You know, they just make that really high-pitched whistle when they run. It's a high-pitched whine. So by using that resistor in series, they've nudged that down, and it just runs at a sort of lower speed and quieter. The fan blows air from the back of the circuit board. It blows it through these holes. But it also blows it through this little ceramic tube, which is the ozone generating component. And the air is actually pulled in the back of the unit here, blown through, it's mixed, it partly goes through these holes to give a greater airflow, and also that to add the ozone, and then it comes out this little hole in the front here. The circuitry for stepping the voltage up is a bit strange. Let me bring in my notepad and show you this. It's based around this 555 timer chip Very simple, and all it's doing is it's driving a MOSFET. Then you've got the positive connection goes through a inductor, that's this inductor here, then through the primary winding of this, which is just a smallish number of heavyish turns in the transformer. Nice transformer, by the way. And then it goes to the MOSFET and gets switched to the negative rail. Let me show you the circuit here. I'll just tame this down again because it looks a bit ferocious. Here's the odd thing. I expected when they turned the switch off, you know, when you turn the knob on the side of this down, it does physically click at the end. I thought that would kill everything. I thought it would kill the ozone generator and the fan, but it doesn't. The ozone generator continues running in the background. You can actually hear the very slight hiss of the corona discharge in here. I would be concerned that if you left this plugged in all the time, but turned off on the knob down to the point it clicked off, that the build-up of ozone inside without the fan to blow it out could actually start corroding some other components and causing damage to the unit. But I suppose time will tell on that. The 555 has the usual configuration for an astable oscillator. It's got the pins 8 and 4 connected, pins 2 and 6 connected. The negative connection is to pin 1, the positive connection is to pin 8. We've got a little capacitor, 100 nano, connected from pin 5, which is reset just to reset the chip at power up, make it more stable, I guess, as well. And then it's got the classic arrangement of a 555. Normally you just have a couple of resistors and a capacitor. But in this case, they've got a couple of resistors in parallel. They've got a 1100 ohm 1K1 resistor in parallel with the 1K potentiometer on the knob. And that means that the value of that resistor will vary between 0 to about the combined value of those in parallel, which is about would give about 500 ohms. And it's in series with another 510 ohm resistor to limit just how low it can go. So that can go effectively from about 500 ohms, say, up to 1000 ohms with that combination, just depending on the position of the knob. You've got the other resistor that forms the other part of that sort of resistor pair, and then you've got a 10 nanofarad capacitor, which ultimately sets the frequency. The output from pin 3 is pulled down to the negative rail by a 100k resistor to make sure the MOSFET turns off okay. I've drawn a lazy MOSFET here, I haven't drawn the full thing in. But it runs the MOSFET at a frequency of, when it's off, 29.6 kilohertz with a 54% duty cycle. I used a little LCD oscilloscope to measure this. I should go and get that oscilloscope. One moment. My little LCD stunt oscilloscope, it's used in applications like this where there's there's several thousand volts on this circuit board, and I don't want to blow up a Keysight oscilloscope, but it also means that I don't have to get the oscilloscope out and put it in here. This one's very convenient, it's a wee pocket-sized scope. It's a DS212. I bought it from Banggood, I think. After doing a lot of research, it seemed one of the easier ones, but I have to say, its main operation is by two thumb wheels, and the top thumb wheel adjusts variables, like for instance it's adjusting channel A's, the voltage threshold per section of the display reticule, and the one at the side scrolls up and down the menus, but you can also click the buttons, and it's just, I've got it fairly recently, I'm just getting used to it at the moment, because as with all these little tiny oscilloscopes, you have to get used to the menu. So, yeah, it's this MOSFET is running at those frequencies. Full was off was 29.6 kilohertz, 54% duty cycle. Full was 26.9 kilohertz, 60% duty cycle. And the waveform was roughly on the oscilloscope. It was going, when it went up like that, it would tail off slightly. I don't know if that was just the initial impedance of the inductor and then the voltage of the supply falling. I'm guessing it probably was that was causing that. But this was roughly the shape of the waveform, just a slight slope down, not quite a perfect square wave. So we've got the inductor here in series with the winding, and it's quite, I wonder why they've put a secondary inductor in series with the inductor of the actual transformer, the high voltage transformer. That's strange. But there it is, there's the inductor, there's the primary of the high voltage transformer. Then the secondary is divided into 5 sections. The reason they've divided it into 5 sections is because the split secondary transformer lets them keep the voltage across each one of those windings down to a lower level, and then it puts a solid plastic barrier between them. It just makes it much more reliable. I could have shown you that on the actual bigger transformer here. So there's effectively the barriers between each of the secondary windings. So it lets you add up to, say, you had 1,000 volts across each winding, it will let you add up to 5,000 volts. But whereas if they were all in the one bobbin, you'd then potentially have 5,000 volts between one end and where it passed the other end, where the coil came from the outside. Where the wire came in, it's when you wind the transformers, you sometimes get overlap of the windings. So this is just a way of actually keeping them well separate. And the whole thing is vacuum potted in resin. It's quite a good transformer. So that puts out the high voltage at high frequency, which will be 29.6 or 26.9 kilohertz. The ozone is generated by the standard corona discharge technique. Something I didn't mention there was this capacitor here. This is a class Y capacitor, and it's hooked across from the low voltage secondary of the switchmode power supply to the primary of the switchmode power supply, and that just couples noise back that could be coupled through the windings of the transformer. The way the ozone is generated, if you get a couple of connections with high voltage between them, then if you were just to simply have two electrodes placed next to each other, you'd get a spark would jump across between them. So what they do is if you put an insulator between the two of them to stop that happening, you end up with lots of tiny little sparks instead, which basically forms a corona discharge. And the sparks aren't physically jumping through material, it's basically capacitive coupling from one side to the other. So what they do here is they get a ceramic tube, and they wrap copper foil around part of it. So let's see how they've done that here. Okay, so it's at the output side, they've wrapped the copper foil around, and it looks like a standard piece of copper foil tape that they've just wrapped round, and then they've placed it through the hole in the circuit board. Say this is the circuit board hole here, and then they've soldered it onto the copper tape. That doesn't just hold the copper tape, it makes the electrical connection onto the copper tape, holds it all securely and holds the ceramic core in place. Then they've got inside this, they've got a stainless steel strip coming in like this, and then going out the end. And you can see that, where is it most visible? There's the end of the ceramic tube that's well away from the copper tape. The copper tape, this is where it's soldered in this area here. Let's brighten that up again. So this is where it's poked through, and then they've soldered it. So that's one connection. It goes to one end of this transformer. This is the high voltage secondary of the transformer. That is the high voltage primary of the transformer. And this is probably stainless steel strip, although they've soldered it one side. I don't know why this didn't solder it all the way around, but I wonder if that is, I wonder how well it takes solder. I could try it with solder. But it is either way, it's going to be, it doesn't attract a magnet, it feels quite hard, so I would say it's probably a stainless steel. And the reason they've chosen that is because there are very few metals that survive exposure to ozone. So what's actually happening here is that is the, turn this back down again because the paper is quite bright. Where this metal strip touches the inside of that then forms the capacitor. That is the conductive coating on one side and the metal strip on the other, and that will have a corona discharge on the inside of the tube where that is, because it's the one that's got the sort of largest air gap between that metal strip. There won't be corona discharge on the outside because it is just basically solid layer of copper on the outside. So just where that goes into the tip, that just creates a slight purple glow and a corona discharge, and that will vary depending on the setting of the knob. And the air flows through and it carries. Because the corona discharge splits oxygen molecules apart, this is where I can never remember, is it oxygen atoms? Or is it splits oxygen molecules apart? I think it's molecules. But it splits them apart and then they recombine. Normally, oxygen is just stable as two oxygen molecules bonded together. No, that a molecule of oxygen is two atoms of oxygen, isn't it? I can never remember. Either way, it splits them apart, so you end up with free oxygen, and they sometimes form into unstable clusters, like O3, which is ozone. And that is, because it's unstable, it wants to get rid of one of those oxygens. So it wants to go back to its stable state, which is O2. So it will oxidize things. And that's why it smells like bleach. It's basically the bleach of the air, so to speak. It's got a very, very strong smell. The name ozone is actually derived from the fact it has such a strong smell. So that's more or less it. It's basically... to break it down to its modules, it's got the suppression circuitry, it's got a 12-volt power supply, it's got the oscillator that runs the transformer, and then it's got the corona discharge, and that 12-volt supply also runs the fan. And the knob just simply varies the frequency, it appears. And I wonder if the frequency control is to do with inductor, and the higher the frequency, the less current will effectively get through the inductor. So everything must just be perfectly balanced for that application. And as I say, if you have one of these, I would recommend that when you turn it off, don't just turn it off the unit. The green LEDs will stay on because the 12 volts remains on all the time. If you want to turn it off properly, unplug it, because that way you're not going to end up with the corona discharge all the time. Which I don't know if this is a design feature that, it puts out trace ozone, because there's certainly no air blowing it out. Or if it's just a design error, maybe, that they just didn't switch or maybe the current rating of this switch isn't enough to actually switch the ozone generating section. It doesn't seem that high a current. It seemed quite low. Or maybe it is just, they reckon that, that small, tiny trace level of ozone is absolutely fine in the background, although, it could affect the components inside because it will build up in the case. Interesting. So there we have it. It is just basically, it's not an ioniser at all. It just basically creates a continual flow of air out this hole with ozone in it, and that ozone then breaks down odours by oxidising them, and it kills bacteria and stuff, and yeah. But at very low level, just so it's not really so much of a health problem. This is a controversial area, because some people say any ozone is bad for you, and others say trace ozone is fine. They used to use the ozone generators like these in public toilets, just as an alternative to air freshener. It just kept the place smelling fresh. It got rid of bad odours by oxidising them. But the concern there is that it's all right for if you're just going into the public toilets and use them and then you're leaving again, but the people who work in them and maintain and clean them, they're exposed to that all the time. So maybe not such a great idea. But there you have it, the Puripod ozone generator. It's quite neat inside. It's properly designed. It's quite a good quality device, but it is ultimately an ozone generating air freshener.